This is a rough timeline. In the last 100 years, the sea level rise based on tide charts in our area has gone up about 8 inches. Okay? So 100 years, 8 inches. Okay? In the next 15 years, we expect sea level here to go up by 6 inches. So we're going to do nearly 100 years worth of rise in 15 years. Okay? In the 20 years after that, we're expecting sea level to go up at least 2 feet. Okay? And so part of what we're going to be talking about tonight is sort of, why these numbers, where they're coming from, what some of their impacts are likely to be, and sort of the speed of change and why this seems to be changing so fast. Okay? First, I want to go back and lay in some fundamentals for this whole thing. So let me start there. So what are some of the fundamentals? What's some of the science? What's some of the changes that we're going to be seeing? The couple of quotes here. Greg Bateson talks about the fact that the major problem in the world are the results of the difference between how nature works and how people think. Okay? We want it to do this, it actually does that. Okay? And then Steer, who was the executive director of the United Nations Environmental Program for a decade, talks about the fact the environment can be humanity's greatest friend, or if poorly managed, our most implacable foe. Okay? This is the scenario we are trying to avoid. Okay? Our heads in the sand as the water rises around us. Okay? This is a quote I like, that climate is an angry beast, and we are poking it with sticks. Because that really is about what we're doing these days. We are adding a tremendous amount of carbon to the environment, and so it's trapping a great deal of heat and causing sea level to rise and a whole series of other things to happen. But for people who want to know whether or not climate change is really happening, global warming is really happening, I'm just going to show you part of this. This is a NOAA and NASA clip of temperature changes between 1950 and 2014. And the more reds and oranges you see, the hotter things are. So we have, in fact, made it much warmer. I could show you the whole series from 1880 to now, but 1880 to 1950 look pretty much the same. This has been a relatively recent phenomenon. We sort of kicked over into accelerated climate change back in the late 70s, early 80s is really when we started to see all the numbers take off. Is climate change human caused? And the answer to that is yes, it is. Part of it, I know we get wrapped up in this conversation about carbon dioxide, and people go, well, it's natural, it's what flowers make and trees make. Yes, but not nearly as fast as we do. But the real issue is the fluorinated gases, chlorofluorinated gases that are involved in climate change. These are not natural. They are all man-made. So you want to have some idea whether or not people are involved. That's definitive in and of itself. Okay? If we look at how glacial cycles have worked in the past, essentially what happens is the Earth goes from a fairly circular orbit to a more elliptical orbit around the sun. And it takes 100,000 years thereabouts for this cycle to complete itself. When it's more circular, average temperature goes up. When it's more elliptical, we have cold zones. Okay? All the data that we have suggests that back in 1970, we should have started to see climate cooling. That is when we were going back in the elliptical orbit, and we should have seen temperatures start to drop as opposed to seeing them rise, which is what we saw. There's also issues of what the tilt happens to be of the planet, and then how much we wobble on our axis. Both of those things play in to how much heating or cooling takes place. But the big driver is the orbit itself. And then when the orbit changes, what happens is temperature goes up, and then that triggers changes in carbon dioxide. What's happening now is carbon dioxide is going up, and that's changing changes in temperature. Okay? Part of the way that we know that this is about human activity is that carbon has 3 isotopes: carbon-12, carbon-13, and carbon-14. Carbon-14 is the one that everybody likes relative to dating systems. This is the radioactive one. So if you want to know how old a bone is or a piece of cloth is, you look at the amount of carbon-14 in it, and that'll give you a way to age the material. As far as C12 and C13 are concerned, these things are in a ratio of about 99 to 1. And it's important to understand that fossil fuels are biological in origin. Okay? Algae, plants, animal matter that have been changed through geological process to become the fossil fuels, become natural gas, to become coal, to become oil, to become bituminous material. And because they are organic in nature, they have a very high percentage of carbon-12. Atmosphere plays with carbon-12 and carbon-13 equally. It doesn't care what those things are. It just deals with them the same. Plants, however, have a strong preference for carbon-12 over carbon-13. And so when you look at biological material, it has significantly more carbon-12 in it than carbon-13 than you would expect simply by what's in the air to be able to breathe. So when we burn these materials, we release proportionally more carbon-12 than we do carbon-13. And so this ratio tends to shift with the amount of carbon-12 per carbon-13 increasing dramatically. And so since what we're seeing in the atmosphere is a marked increase in carbon-12 disproportionately to carbon-13, that tells us that the carbon that's causing us the problems is the carbon that's burning from fossil fuels. Clear enough? Fair enough? Okay. And so the functional cause of these events of climate change and global warming, sea level rise, extreme weather events is, functionally the increasing levels of greenhouse gases. Okay? The true cause, from my perspective, is humanity's sort of silo thinking and our disconnect from the world that we're dependent upon. We simply don't think about where does stuff go. I know that I want electricity, so somebody has to generate that power, but we don't ask really where it comes from. We don't ask what happens when you burn it. We don't ask where the waste goes, as long as the lights come on. That's sort of our silo in here. And so what we're really looking at these days is how do we start looking and having a broader discussion to look at the full range of implications of using any particular fuel. What are all of its pros? What are all of its cons? What are all of its impacts? And deciding from that full panoply of information what's the best way to go with fuel. Also keep in mind that if you're burning oil, wood, charcoal, natural gas, oil, none of that gives you electricity. Okay? If you don't believe me, next time you're at have an open fire or using the grill or the barbecue, take a light bulb out and hold it about 18 inches off the grill and see if the light bulb turns on. And the answer is it doesn't. Okay? All that stuff does is it gives us heat. We then have to boil water to create steam to turn a turbine to spin the magnets to create the electricity. Okay? So even though we talk about these fossil fuels as sort of the generator of electricity, understand they aren't. There's a whole series of steps that have to happen before that gives us electricity. Okay? So functionally, you believe everything is designed and acting together, or you don't. I mean, that's fundamentally where we are. And this is what happens when you functionally don't believe that. This is a frog with 6 legs, which is not the natural biological design for frogs. And Florida is one of 34 states that have such multi-limbed frogs from, in this case, pesticides and agricultural waste breaking down and causing some problems in these frogs when they metamorphose. So how does this work? How do we get the higher carbon? Pre-industrial revolution, basically carbon cycled. The carbon that went up in the atmosphere or escaped from the ocean basically was balanced by carbon that was being pulled out of the air and carbon that was being sequestered in the ocean. Okay? So that's pretty much the way it worked. We've always had carbon dioxide in the atmosphere. That's why we have the nice planet that we live on. Functionally, we had 730 billion tons of CO2 in the atmosphere pre-industrial age. That's what gave us a thick enough blanket that we could have a relatively stable climate that we did. Okay? And that carbon dioxide just kept cycling through the system. What we've done since then is we have been increasing the amount of fossil fuels that we are burning. So that's a new addition. We have been increasing the amount of carbon dioxide and greenhouse gases that are coming off the landscape, in that the part of this is twofold. One is that as we take living landscape and convert it to hard pack, roads, buildings, sidewalks, and take out the biological component, sterilize the soil through some of the heavy-duty industrial agriculture we don't have anything to be generating and capturing the carbon dioxide. So that leads to more carbon dioxide going up. And we're pretty much at the level of what kind of carbon dioxide we can put into the oceans. We're already changing the pH of the oceans, making it more acidic. We've warmed the oceans enough that we're actually increasing the amount of methane that is coming out of the sediments in the environment. So this is where we're starting to get more of the carbon dioxide that's coming in. Now, historically, if you look at the last 60 years, thereabouts, of carbon dioxide cycles, this is the famous Mauna curve graph, the Keeling curve. And what you see in this is an area of peak in a year and a low point in a year. The peak is wintertime, when most of the vegetation is off plants in the northern hemisphere. Northern hemisphere has more of the vegetation than the southern hemisphere does. So northern hemisphere is the driver. So when it loses its leaves, more carbon dioxide gets in the atmosphere. When the leaves come out, it starts to absorb some of that carbon dioxide back down. But the reason this keeps going up is the amount of material we keep releasing and keep curtailing the amount of material that's available to sequester carbon. Okay? So what does this look like? I'm just going to play you part of a year. And again, in this video, as things become more orange and purple and things like that, more colors that you really don't want to see, that gives you some idea of the increase, seasonal increase, the maximum increase in carbon dioxide that we're putting into the air.
That's February.
Yeah, this is February. I think this runs to part of March, maybe the first start of April. And then, okay, so you can get some idea of sort of the darker bands in here to give you some idea that we've captured a tremendous amount of carbon dioxide into the atmosphere. Also fairly important to notice is that, notice it's northern hemisphere where most of this loading is taking place. And the southern hemisphere is not doing much loading at all, okay? And so this may explain why when we have international conferences to try to resolve this issue, you have one part of the world that seems to be blind to the issue, and one part of the world that says, hey, clean that mess up, okay? Because it really does divide itself pretty much north and south. Okay? So again, all we're really doing is increasing the blanket that we have of greenhouse gases to trap more heat. Just to give you a sort of a different perspective of it, you saw that stuff moving in the upper atmosphere. Now what you're going to see is it stacking up. This is going to be a three-dimensional view of how much thicker that blanket can get over time. So again, you get some idea of how this stuff starts to get stacked up, and again, where most of it is bulking up, okay? So historically, when we're, as humans, relatively new and doing civilization, basically carbon dioxide was about 280 parts per million. I think today, well, at the end of January, it was 406.07. And so clearly we've added a tremendous amount of material. Right now we're really somewhere in the neighborhood of about 1,250 gigatons of carbon dioxide in the atmosphere, basically about 500 tons more than we were when we first started. Okay? And that's where the heat trapping comes in. And so if you want to solve this problem, at some point, not only do you have to stop putting carbon in, you got to figure out how to pull carbon out. We'll show you why carbon gets so much attention here in a moment, but I just want you to understand that carbon dioxide has a potential warming effect over a 100-year period of a unit of 1. Methane, generally the number used is about 21 times, so 1 unit of methane traps 21 times the heat that 1 unit of carbon dioxide does. Okay? Nitrous oxide, this is agriculturally related, the way we farm, about 310 times more than carbon dioxide does. You get into the carbonated fluorocarbons, chlorinated fluorocarbons, and you're looking at anywhere from about 140 times what carbon does to nearly 24,000 times what carbon dioxide does. Okay? So there are differential heating mechanisms. And because sometimes the numbers don't help a whole lot, I've decided to give it to you visually. So there's carbon dioxide, that one little dot. There's methane. There's nitrous oxide. And there are the chlorofluorocarbons, all this times 20. So those things really do pack a lot of heat. So why do we focus on carbon dioxide if the other gases actually trap so much more heat? It's a volume issue. Right now, we put in tremendously more carbon dioxide in the air than we put in the other chemicals. So far this year, we have put in over 4.3 billion tons of carbon dioxide. Okay? Since the 1st of January, we've already done that. So we're on a curve at the moment that by the end of this year, we ought to have put in about 37.8 billion tons of carbon dioxide into the air. Okay? Now, billions of tons means nothing to anybody. Okay? None of us can wrap our heads around numbers like that. So, time for artists' visual translation. So, 4-ton African elephant. You want to get that much carbon dioxide in the air, you got to launch 300 elephants per second into the air to make that happen. I firmly believe that if you saw 300 elephants being launched in the air per second, you would ask all kinds of questions. Okay? And if you saw those elephants just floating up in the air for decades and centuries and millennia and more of them every single day, you'd have a whole series of questions about what are they doing up there? You know, what's going on? Is this really a good idea? Where are they going to land? I mean, all kinds of things are going to come to your mind that because carbon dioxide is outside our range of perception, is odorless, tasteless, colorless, those questions just fade away, okay? Now, 2016 was so far the hottest year on record, okay? The previous hottest year on record was? 2015. And the previous hottest year was? 14. Okay, so, you know, we seem to be on a trend here which is not working in our favor as we do this. And not only are we making sort of the whole atmosphere, you know, hot and land hot, I mean, it was 117 degrees in parts of Australia this weekend, okay? We're also making the ocean very hot. I know science is generally very specific about, you know, we've come up with all this great terminology for things. This just referred to as the blob, you know. It is just a very hot patch of water, and it's not quite clear why it should be there, but it is. So we're warming up the ocean as well, okay? So keep in mind that with climate change, it changes everything, everywhere, simultaneously and synergistically, okay? So we increase levels of carbon dioxide, and that starts to promote things like sea level rise, extreme weather events, climate change, global warming. Those things then feed on themselves to make that matter worse, and then each one of them goes off and sets on its own series of separate events. Okay? You know, so at some point, if we really want to get things under control, we're going to have to come back in and deal with the real source of the problem. We try to mitigate these things as much as we can, but you know, at some point, you know, you just got to actually deal with what the problem is. Okay. So, why does sea level rise? Two reasons, basically. One is thermal expansion. Water is at its densest at 4 degrees centigrade. Okay. This is why, you know, ice floats. If water were at its densest at 32 degrees, all your ice would be at the bottom of the glass. Okay. But you know, it's at its densest at 4 degrees centigrade. And as oceans warm, then water expands. And that just adds to the overall volume of water that you're dealing with. Okay? So if I start making the ocean really hot, and the hotter I make the ocean, the more whatever water is there expands. Okay? The other thing that happens is the calving and melting of land ice. If I'm taking ice from the land and putting it into the water, that adds to the volume of the water from the ice, and I also get thermal expansion. If I'm melting sea ice, when I melt the North Pole, which we're doing right now, basically what happens is that only raises water level as it expands, because it's already in the water. When I take glaciers in Greenland and calve them into the ocean, then I'm getting both extra volume and extra water to expand, okay? And keep in mind that there's only one ocean, so whatever is happening someplace is going to affect everybody everywhere anyway, okay? Now, what you're looking at here are some moulins, these areas of melt in glaciers, okay? And what happens from time to time is that these freshwater areas, these moulins, get stream flow, and that flow can come all the way down through a glacier all the way to the bedrock. And when it does that, it allows the glacier to slide faster. Okay? It lubricates the bedrock and just lets that ice slide. Okay? And so part of the reason we see an increase in the rate of change is the faster this can slide, the faster this stuff gets into the ocean, and the faster it makes changes. Okay. This is a graphic of the reflectivity of the Greenland ice sheet. Basically, what we're looking for is a high amount of reflectivity. If Greenland is ice covered and it's white, it reflects a tremendous amount of sunlight. The more meltwater it has, the more melting that's going on, the less white it has, the less reflectivity it has. And so this is a fast way for us to get some idea of what is happening, how much of that surface is melting and where that water is going. And as you can see, for the last 12 years, the system has been in decline, that we got more melt and less reflectivity, okay? Now, rising sea level isn't new. The planet's been doing that a long time, okay? What's new is how fast it's happening, okay? That's the real kicker here, okay? I mean, we're taking 1,000-year timelines and compressing them into centuries and decades, okay? And that's a huge problem because it doesn't give anything time to really adapt to how fast that change is taking place. If it was going to take 5,000 years to raise, water level 6 inches, Miami would not spend a dime on this stuff. Because over the next 5,000 years, it's pretty easy just to, phase that kind of change in, okay? But Miami spent over $300 million to improve its infrastructure because that's how fast stuff is changing, okay? The other thing that's new in this is that this is the first time it's happened to us, okay? We haven't been around when this has happened before. Modern humanity's only been around for 200,000 years. The last time we had sea level, CO2 levels this high was at least 800,000 years ago. We don't have anything to model from or compare it to, okay? So we're basically the cause of what's going on, and we need to figure out how to be the solution. Now, over the next series of presentations, mine and other people's, you're going to see different projections and different numbers being used. And that's fine. This is what science is all about, okay? How fast do you think sea level is going to rise? So what goes into this calculation? How fast is temperature changing? How much is it changing? How much does that affect the ice? How much of that affects the ocean? Okay? If the land is warming up or the air is warming up pretty fast, but the ocean's warming up very slowly, I don't get as much thermal expansion. If the water is warming up pretty fast, I get a lot more thermal expansion. Okay? And so trying to figure out how fast ice will melt is really what the puzzle happens to be. And again, part of this is, as I start to melt ice in one place, I lose the reflectivity, so I increase the melt rate. And so people are trying to figure out which model works best. And there is also just a functional, to a certain extent, political, aspect of this, and that is, if I'm an elected official, what number can I get anybody to believe? Okay? I mean, if it took 100 years to raise local sea level 8 inches, and I'm going to go out and tell my constituents that by 2050 we're going to have 2 to 4 feet of water, people are going to look at me like I have 6 heads, okay? I'm a scientist. I'm used to that. Politicians are not, okay? So we have sort of different numbers being used in different parts of Florida, depending upon what everybody sort of can wrap their head around and agree to at any one particular time. But these numbers are constantly changing, even as data comes in. For example, in 2013, people were saying that the maximum estimate for sea level rise by the year 2100 was 3.2 feet, okay? The following year, 2014, people were talking about, well, we're going to have at least 11 inches of increase in water height by thermal expansion. We're probably going to be looking at about 4 feet of sea level rise by 2100. The range is up to about 6.6 feet, okay? So in 1 year, we went from 3 feet to 6 feet, okay? Then In 2015, we went from 6 feet to 10 feet is the maximum, okay? So in 3 years, we tripled what we thought was going to be the high water, okay? And now, in, where is it? Okay, in 2016, must have lost it someplace. In 2016, we start to see Antarctic water melting, the Western Antarctic ice sheet melt. And the response to that has been, whatever of these numbers you're happy with, fine. Just add 5 feet. Okay? So take whatever you want and just add 5 feet and figure that's where we're going to be. Okay? Now, I don't know how they got away with this, but I really do like the fact that Oceans Melting Greenland, was able to get the "Oh my God," logo as its acronym. Okay, and essentially what's happened is what we're talking about before was surface melt. Okay, now what we see is that sea level has risen enough that we're getting water coming in underneath the glacier. So not only do the moulins come down and apply fresh water, but we've got ocean water coming in and reacting with the ice as well. So it's actually being carved from both sides underneath, as well as the melting on top. And that's where these extra projections are coming from. So there it is. In 2016, add 5 feet. Okay. So in 2016, this is when we started to see all the information about the West Antarctic ice sheet and how fast it could melt. It really has been, quite dramatic as to what that level of increase is going to be. They're looking at 5 to 6 feet by 2100. Okay, so we're talking about this area right in here, especially right in here. Okay, and these are the 6 glaciers what people are monitoring right now to see how fast this ice sheet is going to let go. This is land ice at the moment, but see how fast that lets go and starts changing things. And so when we did our event out on Siesta Beach, which you'll see the video here in a few minutes, we were using the 6 to 10 inch numbers for the 2030 part of the display. But we've already moved to the West Antarctic numbers for what's going to happen by 2050. So you'll hear in the tape, we did, here's 8 inches, splitting the 6 to 10 difference. And then here we are at, 2 feet, okay? And that's why those numbers come in. Because we're seeing some things parallel and also a little bit different in the Antarctic. We are getting ocean currents that are undercutting the glaciers. We're getting surface melt on the glaciers. We're also starting to see fissures show up in these glaciers. Normally what happens in Antarctic glaciers is they fissure on the edge, okay, on the ocean edge. Now what we're seeing is some of these things are starting to fissure in the middle of the glacier, which means somehow those glaciers are melting from the inside out. Okay? And that's where the predictions get very tough to do, because it's really tough to measure how much ice isn't there when it's sort of deep inside some of these things. But sort of the take-home story here is basically that that climate change is calculus, not algebra. It isn't about changing shape. It really is about the rate of change. And that here's the Pine Island Glacier, and between 1994 and 2007, this thing had melted more than 90 meters of ice off the top of itself. Okay, I mean it's still a massive glacier, but it's getting a lot shorter here. And this is Pine Island as it sort of fractures in the middle. Okay, so previous to this, we've done a project flagging the tides. We did it at Lido Beach, we did it at Siesta. So here is Siesta on a, I'm sorry, this is Lido Beach on a very nice day. Okay? And this is Lido with a 6-inch storm surge when the last tropical storm came through. And so to put this in perspective, you're starting here down at the beach line, and where you saw those little tufts of grass is this stuff right up in here, okay? So with 6 inches, you're functionally losing Lido Beach, but you're certainly losing the first 285 feet of it. And so, you know, we're a beach economy right now, and it always occurred to me that you actually needed a beach to be a beach economy. And so the question is, you know, what are we going to do? And so some of this is about, you know, what is the model? And part of what I want people to keep in mind is that with climate change, we can't look backwards at what has happened because the rates are just too different. We have to think about what the projections can be and how do we want to deal with those projections as opposed to thinking things are going to sort of slowly happen here. Climate change is going to change temperature, weather, coastlines, rivers, land formations, water supplies, food availability, ocean currents, toxicity of bacteria, acidity of ocean vegetation patterns, livestock survivability. Everything is in play. Okay? What type of changes we're going to see here? We're going to see changes in rainfall patterns. We're going to have longer periods with no rain, followed by major rainfall events. Okay? We're going to see change in evaporation patterns, especially during the dry areas. So we're likely to be able to trigger more droughts. We're going to have increased air pollution, and we're going to have an increase in heat-related and trigger deaths and illnesses. Okay? I don't think these are things we really want to have play out. And so the question becomes, again, what are some of the things we're going to try to do? This chart here is basically looking at, and this is now out of date because of Antarctica. It's about 2 years old. But basically it's looking at, okay, by 2029, what is being seen as extreme weather now in Lagos will just be the weather. Okay? What's extreme weather today by 2030 in Cairo will just be the weather. And right now, that's the conversation we're having is all the extreme stuff the places are seeing is on its way to just be the weather. So changes in food, it's going to change the quantity, quality, affordability, diversity, and where, when, how food can be grown. Okay? We're not going to be growing the food in Florida that we're growing right now. We're not going to be growing that stuff locally. We're not going to have the weather pattern or the temperature that allows us to do that. We're going to have to find a whole new crop, so we want to keep this part of agriculture going. Okay? We're going to need cisterns and gray water systems. Okay? Part of this is about we need to be able to supplement our water supply. We need to capture rainwater when it does happen to be part of our water supply, as opposed to having it be street flooding and things like that. And also, we need to start dealing with the fact that we need to match water quality to water use. Okay? I know some people get very upset when their dog drinks from the toilet. Okay? The dog is the only one in the house who gets the joke. It is the same water coming out of the tap that is in your toilet. It makes no difference to the dog. You know, it's just the same water. You know, one's just more convenient height. Okay. Yeah. We're going to see an increase in saltwater intrusion, and so you know, we need to again start using water for what its most appropriate use. Because what happens with saltwater intrusion is as saltwater rises, it pushes more saltwater inland. Okay? So we're going to see more saltwater intrusion. And then given the fact that here in this part of Florida, we rely on groundwater. Okay? So we're pulling water as fast as we can out of the ground. Well, if I am pumping water when it isn't raining, my refill for the water I'm pulling out is either going to come from things like the Mayaca and the Peace River getting pulled in, or it's going to be the coastal water getting pulled in. And if I pull the coastal water in, then all of a sudden my cost of operation for potable water goes up dramatically, because getting rid of salt out of drinking water is a pretty expensive proposition. Okay? So, are we really using water for the things that we need to use it for? Okay? Can we resolve climate change? Yeah, we can. We know what to do. We got some of the technology already. We know what the design solutions are. Okay? They'll get better, and there'll be more of them as things go forward. But we actually do know how to do some of this stuff. Can we afford it? Yeah, we can. The way we afford it is we stop promoting, paying $1.9 trillion globally to subsidize the fuels that are causing us problems, and use that money to actually pay for the fuels that don't cause that problem. Okay? We don't have to change the federal budget. We have to take stuff that's causing harm and switch it over to the part of the budget that does good. Now, I understand that Exxon and a lot of these companies are not going to take kindly to this idea, but nonetheless, the money is actually there. Okay? We're going to need some type of greenhouse gas tax, like a carbon tax, but we need something that covers all of the chemicals, so that we're not having externalities or pollution. I am not against energy. I am not against electricity. I am against pollution is my major thing, and I'm against the use of externalities. I'm against being able to create a harm and not have to be financially responsible for it. Okay? We need to stop fracking and all these other things, because you can't solve this problem by continuing to allow both events to go forward. I can't start doing some good things while I'm masterminding the bad things to keep going. Okay? The XL pipeline to me, the Dakota pipeline for me, completely wrong conversations. It wasn't about whether or not they should go through and where they should go. It was like the fact, if you want to stop climate change, stop pumping the fuel that causes it. Okay? As Edward Markey said about the recent repeal of the stream rule that was designed to keep streams safe from coal pollution, it was sort of the plea was, please protect us, Congress, from having to protect the public. Okay, we do sort of have a dichotomy of paradigms at the moment. Eyes and environmentalists actually do not understand that we have to destroy the planet to have a healthy economy. There actually is no economy without an ecology. All businesses require natural resources, so the only way you're going to have a long-term economy is to have a long-term ecology. But or as the Prince of Wales says, if capitalism itself doesn't take into account natural capital, then we're all stuffed. And when royals start talking like this is a really serious conversation here. So we have to sort of rethink, basically, how we're doing a tremendous amount of things. It's not that we can't do things, we just got to do them differently. We're not going to get rid of electricity, we're not going to get rid of transportation, we're just going to have to do them differently. And we really need to focus on getting the question right as opposed to getting the right answer to a relatively poor question. Are we really asking the right questions? That's where we have to put more effort at the moment. Now, full cost electricity. University of Texas at Austin just released a report last few days where they have gone through and they have looked at the full cost of energy from socket, from the well to the socket. All the direct and indirect costs, looking at public health issues, environmental issues, subsidies, the whole range. And their basic conclusion, especially in the western part of the United States, is solar and wind. Those are the only two things that actually, if you cost them out, make any sense to use for energy. The other nice thing about solar and wind is this is electricity production that does not need water. Okay? You're not constantly in a bind over water. And functionally, we actually need to do full cost of everything. Okay? We actually need to know the full cost of what our food costs, what our clothes cost, all those kind of items. So we actually know what it is we're paying for, what it is that we're supporting, and whether or not what we think we're doing, when we're trying to do good, is in fact doing good. Okay? I get told from time to time that you can't run the world off of solar energy. I'm a naturalist. That strikes me as odd since the planet runs off of it. But if you actually start to look at the numbers, sunlight striking the Earth's surface in just 1 hour delivers enough energy to power the world economy for an entire year. In fact, the amount of sunlight that's hitting the surface of the world is 10,000 times the world's total energy use. Okay? Yeah, you can power the world off of solar. People say, well, the sun's not always out, the wind isn't always out. You see a lot of coal mines in Florida. Okay? See a lot of uranium mines for the nuclear power plants we have in Florida. We don't have those forms of energy all the time either. To run coal power plants, fuel plants on the east coast of the United States, we need a train 35 miles long full of coal to run the east coast for a day. Okay? And we also need an abstinence-only policy for fossil fuels. So we're now in a situation where capture and storage is basically equal or gaining ground on continuous generation and transmission of energy. Okay? We're starting to get the battery systems so that we can store it. We're improving the capture capability of solar. We're lowering the cost of solar. It's actually starting to make more sense. If we go to distributed energy, we also have some greater options, and we should keep it centralized. Right now, in power lines between the power plant and the socket, we lose 58% of the power that's generated. Okay? The world doesn't need more energy. It needs to deliver it in a wise way. Okay? So we need a renewable energy portfolio for the city, the country, the region, the state, the country, and the planet. Okay? That's where we need to go. And in this, we need to really start phasing out the fossil fuel as quickly as we can. Okay? Because this stuff is telling us we're on a really tight timeline. Okay? Every roof must serve. Okay? It needs to catch energy, water, grow food, create habitat, sequester CO2 and air pollution, or any combination of stuff thereof. Sarasota hasn't gotten any smaller since it became a county. It has less habitat than it was when it became a county because we replaced it with buildings. Use the buildings to pay back into the system. We have living roofs and living walls. That's what you're seeing pictures of here. And they reduce the heating of the urban. They break up the urban heat island effect. They mitigate rainwater. They create habitat. They sequester CO2. They provide surfaces for air particulates to settle on, so you reduce your air pollution in the area. They're affordable. They're attractive. Go with it. We're going to, as Ed talked about before, we're going to see changes in sea level height, temperature of the ocean, salinity of the ocean, pH of the ocean. All that's going to change the physical parameters of ocean life, and when combined with the overfishing that we're doing, change the whole balance of life in the ocean. Right now, we are promoting jellyfish over seafood, is basically the way we're handling the oceans. Okay? This is the last scary video, but it's scary, so just be prepared. When this video was originally done, the idea was that you wouldn't see this for about 200 years.
You got to turn your sound up.
Antarctic melts. That's Florida in 2100.
Where's Sarasota now? That's all we care about.
Yeah. So there's Tampa Bay. We're sort of right in here. Okay? So Miami and Tampa Bay are two of two global cities in the top 20 of cities at risk from sea level rise. Okay? And so I'm not sure that sitting between them is really, a great geographical win on our part. If we just look at the top 20 cities, we're looking at 193.9 million people that have to be relocated. Okay. You think people were upset, with stuff out of the Middle East last year, move this many people to town. Okay. And again, all this is doing on this other side is the fact that is remarking that none of what's happening is passively reversible. It doesn't happen on its own. It all takes actual activity to make it happen. The other thing to keep in mind is we can't solve environmental problems by creating social ones. I like to get off of coal. I'm from Kentucky, a coal burning state, coal mining state. If we're going to get rid of coal, that's great, but we got to figure out what to do with the miners so that they still have some type of livelihood and the communities survive. Okay. And along that line, just so keep in mind, that's Earth from space. That's the game we're playing with right there. We don't have another option. We got to make this work because Earth is really sort of the ultimate experience in island living. So, okay. So financially, as we look at what's happening in the world, keep in mind that if you want financial resources for help, we're in financial competition with Miami and Tampa and Jacksonville and all these other cities that are going to be impacted locally, regionally by sea level rise. But we are confronted with insurmountable opportunities. So local farming, organic farming, especially. Organic farming takes care of soil. Okay. I'm not going to argue this on grounds of nutrition or any of that kind of stuff. I'm just selfishly. Organic farming takes care of soil, and healthy soil absorbs a tremendous amount of carbon dioxide. There are some reasonable estimates that you could pull a tremendous amount of carbon dioxide out of the atmosphere just by getting the soil alive again in more parts of this country. Again, we all matter. So it's about all of us. So we're going to be looking at how to prepare infrastructure and dealing with emergency management and prepare for the new economy. That's the post-beach economy. Is my answer to beach renourishment. If you just sort of look at the numbers here for Siesta, in 07, we got 6.5 acres of dune vegetation and 1 million cubic yards of sand for $11 million. Last year, we got 1 acre of dune vegetation. We got 600,000 cubic yards of sand. So we did less, significantly less than we did here, and it cost us twice as much. And it's not going to last as long. So, go pound sand. I mean, this is really all you're doing, expensively, but that's what we're doing. If you want to do one more beach renourishment, fine, but by 2020, it will be obvious to everybody. You're just throwing the money away. And we're also going to see some impact on what happens with real estate values, changes in tax revenues for communities. So what's our operating capital going to be? What are we going to have to work with? Because with every foot of sea level rise, we lose lots of homes. If we're just looking at what we're going to get with Antarctica, that puts 1.5 million homes at risk. So, so things that are alive are what we need to promote: shoreline, seawalls, habitats, organic landscapes. If we're not going to have a beach, let's do some fun stuff. Do a coastal highline, like they have the highline in New York. Do it here, or a canopy walk. Things that will still attract people to the area. Put in a couple of reefs. along Lido and Siesta. We can keep water sports going. It's just, the sport isn't going to be lying down. It's going to be actually doing something. But we can make that work. Currently, we've been designing to promote flooding and saltwater intrusion. Okay, that's an activity we need to stop because this is what's happening just with current rainfalls these days. In terms of flooding coastal roads, overwash on beach areas, in parks and things like that. Okay. We don't want the green algae. We don't want the dead fish. It says it's easy to dodge our responsibilities, but we cannot dodge the consequences of dodging our responsibilities. Okay. And that's pretty much where we are, shifting from being the cause to being the solution. Climate change is the common enemy. And if we actually thought about it that way, we would attack it that way. Roosevelt, in his State of the Union address in '42, talks about the fact that no man say it cannot be done, it must be done, and we have undertaken to do it. These are the numbers that he had for how many tanks and aircraft guns and airplanes and merchant ships we had to build in 1942. We didn't have the capacity to do that at all, and in less than a few months we did. It was an issue, we had to deal with it, boom, we committed to it. We got to get committed to reversing what we're doing. So change our thinking, change our consciousness, change perspective to sort of more planetary view. Think in terms of systems and connections and flows. Where does all this stuff move and how does it go together? Be curious. Ask yourself where things come from. Verify it. What really happens to it. Promote conversation that leads to positive action. Forgive. There is no point having arguments about what has happened. We all played a role. Get over it. Move forward. And think about what it is that we want the future to look like and head there, because that's really what we have to do. Or as Jefferson said, we need to place before mankind the common sense of the subject in terms so plain and firm as to command their assent. And we're the only ones that can do it. So, thank you very much.